So I hope my screen is visible and sound is audible. So we are here for the week 10 live interaction session. So it's- so in the last week we did assignment 7, and this week we are supposed to do assignment 8. So in the last week, we discussed what is a category and some definitions related to category theory. So week 8 concerned about the functors and some properties of functors. So do you want me to revise a bit from the last week's lectures? Hello. So shall I just revise what is a category and then start? I think. So, once again define what is a category. So let me just revise. So the first
Sir, what is the
definition.
means of category that I want to know?
Okay, so actually, category theory is an idea to discuss a collection of objects without going into the detailing of those objects. Means say as a group set of means collection of all groups forms a category. So you can discuss many properties of groups uh, as a whole without actually concerning uh, even the definition of groups. You can say you don't need to work element wise. You can work as a whole, considering the category of groups, and whatever result you can obtain, that is implementable to each and every group. So that's maybe one of the reason that you can work with the entire collection rather than focusing on the single object at a time. Okay, so that's one of the application that I personally think is there while discussing the.
Means it's just like a property in the collection of sets.
So I didn't share my screen.
Is it?
I didn't share my screen, right? Okay, sorry. Now it might be visible, right?
Yes, sir.
Okay. So I was just saying that you were asking something, Vivek.
Yes, sir.
I
Means categorize is like some properties or collection in the sets.
not even sets. I will say.
Some
Let me
particular
just
properties.
recall the definition of a category, and maybe then you can relate more. Okay. So
Okay.
what is a category? So a category. C. So let's. The notation is maybe C, consists of first a collection of objects So maybe we will denote it by obs of C. Second, so it has certain number of objects. It may be anything. Okay. And second is for all objects, say maybe A comma B of C, a collection C of AB consisting of arrows from A to B. So it has a collection of objects, and for each pair of objects, a collection C of AB, which maps A to B. So arrows from A to B. It's not a map, because when I say map, then that the first thing that comes to your mind, that A is a set and you are mapping each element to of A to the B. But I'm not saying that A is a set or B is a set. It can be any object. It's a collection of objects, and such that one from one object to another object, you have certain arrows, well-defined arrows, and those arrows are there in the collection C of AB. Okay, and the third thing is for objects, if you have three objects A, B, C of C, a composition C of AB, sorry, a composition function. So if you have three objects A, B, and C, then there are arrows from A to B, there are arrows from B to C, and there are arrows from A to C. You can actually compose them. There should be some composition rule. So C of AB cross C of BC, from here to C of AC, there should be well-defined map. So C of AB contains arrows from A to B, it contains arrows from B to C, and it contains arrows from A to C. So say F is an arrow from A to B and G is an arrow from B to C, then there should be a composition rule that maps A to C. And in addition to that, so there are three things: objects, or arrows from one object to another object, and then a composition rule for the arrows. Okay, and these collections must satisfy the axioms. First is associativity. Associativity for these arrows must be there. So that, what does this means? It means for all A, B, C, and D objects of C, if say F is inside the collection of arrows from A to B, and G is inside the collection of arrows from B to C, and H is inside the collection of arrows from C to D, uh, then we have the associativity in this composition. That is, H composed with G composed F is same as H composed G composed. So it satisfies the associativity rule, and this is taking, so you F will map A to B, G will map from B to C, and H will map from C to D. So these maps are from A to D. So these are inside A to D. So this kind of associativity rule must be there. And second thing is identity. So says for all objects A of C, there must exist an identity map in the identity arrow. I should not say map, an identity arrow from A to A such that F compose identity of A is F for all arrows F from A to B, 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 and identity compose F is equal to F for all F belongs to the collection of arrows from B to A. So there are objects, there are arrows from each object or other object, and these arrows satisfies the composition rule, and in addition to that, they satisfy the associativity rule and then the identity rule. So with these properties, we say a collection with these properties is a category. So now let's see some examples. So you would be aware with so many examples satisfying these properties. So first example is category of sets. So it is denoted by this notation set underline. Okay, so category of sets. So here the objects are objects are all sets. Okay, whatever sets are there, you will just take their collection. Second thing is the you need maps, right? So for any sets A and B, so here the name of the is set underline. Okay, so it will be the collection of arrows from A to B. So this is equal to uh, set theoretic maps from A to, and you know that for these maps satisfy the property of composition. So composition of arrows is the composition of set theoretic maps. These set-theoretic maps satisfy the composition rule, and so this is the composition of arrows for this particular category, and these maps satisfy the associativity also, and the identity map from a set to another set is called the is the identity arrow. Okay, so it forms a category, right? So similarly, there are other examples. Other examples are uh, uh, so category of groups. So here the sets are all here the objects are groups, and the Arrows are group group homomorphisms, and composition is the composition of homomorphisms. Similarly, category of rings you have, ring homomorphisms are the arrows, and their composition is the composition rule. You have, you can consider the category of fields, right? So it will be just uh, all collection of all fields, and the morphisms are field homomorphisms, and the composition is the composition of field morphisms. Okay. Now I won't discuss some other example because that's already been discussed in the lecture, and we don't have that much time. But some properties that I want to discuss is uh, so there is something called apimorphism and uh, monomorphism in categories. So that I think I should define. So an arrow F belongs to the set of arrows from an object, say B to C, is called a monomorphism if for all G comma H arrows from uh, A to B whenever whenever f of G equal to f of H, uh, we have G equal to H. So what is saying that you have arrow from uh, an arrow from B to C. So that arrow is said to be a monomorphism. If you collect, if you have arrows from, so say there is B object, there is C, and there is A. So you have an arrow from B to C F, that is F, and so that should be for all G and H belongs to C. Whenever f of G equal to f of H, we have G for all A inside object of C. So for any object you considered, that is A, and you consider the maps from A to B, any two maps, uh, G or H. I'm saying maps, but they are just arrows because they are mapping the entire object to the entire object A to B, not element wise. Nothing is element wise in category. First of all, you should get rid of that common practice that we use arrows and as maps in general practice. But when we are considering the category theory, we should get rid of that ideology that these are arrows, these are maps. These are just an arrow which maps the entire object from A to entire object. That's it. Okay. So what I mean by an monomorphism is you have an arrow from B to C. You consider any other object that is A, and then you have two arrow from A to B, that is say G and H. Then whenever you have f of G is equal to f of H, because you can compose them, it's a category, so the composition rule is there, then this G is equal to H. So this F somehow plays the role of cancelling, right? If f of G is equal to f of H, then you can cancel this F, and you have G equal to H. So that is the definition of monomorphism in a category. And similarly, you can define an epimorphism. I hope that is fine. So yes,
Sir,
yes, wait.
so whether can we say it is a mapping or not in
No,
general word?
see, if in general for category, it's not a mapping, because mapping means you map everything element wise. But A is any object. You don't know whether it's a set or not. It's just a object in category.
So, sir, how can we differentiate in mapping or categorize here?
See, say I defined a category to be just say a collection of students in a class. The objects are a collection of students in a class. Okay, and maps maybe I can define from one student to another student is the difference of heights from A to B, right? So there
Mhm.
you can't consider a student as a set or a collection of elements, right? It's just an object, and the map the map that you are using, sorry, the arrow that you are using in mapping from one student to another student is just the difference of height. So
Collection of
you are actually
something.
mapping an entire student to another student by just the difference in heights. Okay, so it's like a more general theory which covers everything, every collection in every meaningful connection it covers. And for example, I gave you that if your objects are just sets, all objects, you collect the collection of all sets, that is called the category of set. And then
Sir,
there,
here, as you
yeah,
mentioned here, there are two axiom, okay? The associativity and identity property.
yes.
So can we say the mapping we satisfy the two mentioned property, then we can say that map is in categorize.
See, mapping is categorized has no meaning. This collection is named category. You're not categorizing anything. This entire collection with objects and arrows satisfying these properties, this entire collection is called category.
Category.
Yes.
Like a set,
See,
collection of
category,
something.
is the category is a collection of something which
Okay,
which these specific properties. That's it.
okay, sir.
Okay. So, and
No, fine.
we are interested in understanding these uh, collections. Okay. So now for such a collection, I define what is a monomorphism, and then now I will define what is a uh, epimorphism. F from say C of AB is said to be called, uh, called an epimorphism. That's why I told that one should erase every data related to sets while reading this category, because that will confuse you. You just consider them as individual objects. That's it. So if for all uh, G and H from B to C, whenever you have G of F is equal to H of F, this implies G equal to H. So here the thing is a bit different. You have an object A, you have an object B, and you have C. A to B, you have F, and then G and H are from B to C. G and H such that G of F is same as H of F. So you can, if you can cancel this from right, then we say that, and then we say that this F is a apomorphism, and this should hold for all C belongs to the objects of C. So that map which somehow satisfies this left cancellation is called a monomorphism, and the map which satisfies the right cancellation is uh, apomorphism. Okay, so I think that's what was needed. Maybe one more definition I can define from this lecture, and then I will move to the weak eights theory. So again, there is a definition. An object O of a category C is said to be an initial object if for every object A of C there exists a unique arrow from 0 to A. Okay, so an object is said to be a initial object if there exists a unique arrow from that object to every other object of the category. Okay, so that's why it's called initial, because you can all the maps are from you can somehow take it as an initial point of the category, means every other map, every other object has a unique arrow from that object to itself, and with the same split we can define what's a what is a final object. So an object, say the notation I will use one of a category C said to be a said to be a terminal object if for every object A of C there exists a unique arrow and it's a terminal object, so the arrow must be terminating to it. So from A to 1 you have a unique arrow, and for each all objects A you have that. These are some definitions, although they were covered in the last week, but I just recall them for your simplicity. And I don't think that any other definition from the last week is required for discussing this week questions. So uh, week 8 revision we will do now. Okay. So first definition from week 8 is functors. You have to be very cautious while reading this definition if you are reading the category theory for the first time, because it might be a little confusing, but once you understand the uh, idea of it, then it becomes very easy. I will just say a functor. Okay, so first of all, let me just say let C and D be two categories. Okay, so you have two categories. So earlier we were working with a single category, but now uh, what we will do, we have two categories, and the idea is how we can relate these two categories. Okay, so we have two collections, and now you want to relate these two collections. The idea is uh, uh, one can do it using functors. So what is a functor? So functor is an assignment from C to D such that it associates to each object C of this category C, an object FC of D. So it maps every object of C to an object of D. Okay, and then each arrow F from two objects A of B, AB of C in C, an arrow capital F of F inside D of FA and FD. So see, you have first rule is you can associate each object of this first category to an object of the second category, and second say one says that to each arrow from A to B you can associate an arrow from FA to FB. So from A you can map it to some F of A, and B you can map it to some F of B. Then there would be, and then they are objects inside D. So there would be a collection of objects from FA to FB. So you can map this F to such an arrow which belongs to this collection. Okay. So now this functor must satisfying the following axioms. So the first one is for object A of C, F, identity of A. So identity of A is a arrow from A to A, right? And then F can be, this functor will map this arrow to some arrow from FA to FA, and this arrow must be the identity over FA. Okay, so this thing is inside the category D, and this thing was inside in category C. So it must map identity to identity. Second is for arrows A of for arrows A to B and B to C in C, F compose G of F is FG compose F of F. So this uh, functor is called This is called ordinary functor, and there is something which is called the contravariant functor. I will just define that also. Contravariant functor. As the name suggests, it will vary from the ordinary functor by just a little bit. So in the above definition, uh, second is replaced. In second, uh, we have capital F of F belonging to. So here we have this F from A to B. So capital F of F was from FA to FP. But in contravariant, this capital F of F will be from FP to FA. So the direction will only change. Okay, the properties will remain intact. Only the direction will change. Here the map will be from FP to FA, and in B we have F compose GOF is FF compose F of G. Okay. So this is a slight variation we will have. Only the order will vary in second and B, and the rest definition is same. And we say thus it to be a contravariant functor. So there are two kind of functors. Sometimes we require this ordinary functor to relate two categories, and sometimes we require this contravariant functors. And that's it. I think that is good enough to start the assignment. Then is it okay to call ordinary functor as covariant functor? Yes, it is also now known as covariant functor. You are right. So it's just a different name. Okay. So yes. So I will just paste the question number one. Then we will start discussing it. Let me just copy paste. Is there any doubt in that?
No, sir, clear.
Okay. So yeah, this is the first question. So you have two categories. Mon and set. So set I defined. This is the collection of all sets, and this is the collection of all monoids. Okay, collection of all. Okay. So this is a collection of all sets. So which takes so the first one is an assignment which take the monoid to the set M and takes the monoid arrow to the underlying function F. So let me just name them something. This is maybe A, B, C, and then D. Solution of A is, so the assignment is if you have a monoid, then you just map it to the underlying set. You just forget about the properties of a monoid. So this functor has a specific name that is called, it is a uh, forgetful functor. Means the collection of objects, you are just forgetting some property and you are getting the collection of objects for another category. So all monoids are sets, right? So if you forget its monoid property and just consider it as a set, then you can consider take it as an object inside the set collection of all sets. So that's what the functor is. It's mapping a monoid to the set, and the set is, you just forget the property of monoid and just consider it as a set. And the monoid homomorphism is there, so you forget about the homomorphism part, you just consider the underlying set theoretic map, and that is a mapping of this arrow. Okay, so all such functors are all such assignments are functors, and they are known as the forgetful functors. Okay, so first option is correct. You can check that it will satisfy all the properties of functors. The second is f from C to C, which takes each object and each arrow in category to itself. So it's mapping C to C. The object is mapped to itself and arrow is also mapped to itself. So it will also satisfy the property uh, of functors, and it is in particular known as the identity functor. Okay, you're not doing anything, you're just mapping everything to itself. So the third part is uh, let M be the free monoid on two generators and CM be the corresponding category with one object. So in lecture notes, one example of category we saw is the category with one object. We have seen the example of category with one object, and each such category corresponds to a monoid. And you have the opposite also. If you have a monoid, given a monoid, you can define a category with one object such that the arrows are coming from the monoid itself. So for each monoid, you can define a category, and for each category with one object, you have a monoid. Okay, so category with one object are in one correspondence with the monoids, and then it says, so you have given a free monoid, you have to define the corresponding category with one object, and then the functor taking this category to itself be defined on arrows by fm to fm m square. So this uh, arrows here are elements of the monoid, and then the functor is mapping these arrows to this square. This square is inside monoid. So in monoid, you have this composition rule, so that and multiplication rule, and that rule it is using, and then we are to check that whether it's a functor or not. So it's not a functor because uh, there we have seen, let me just write why it's not a functor. So f is not a functor because each functor of a one object category of an one object category corresponds to a monoid homomorphism. And in general, uh, Fm equal to m square is not a monoid homomorphism. For example, you can take a group in particular because every group is a monoid. So for that group, this uh, squaring map is there are many groups for which squaring map is not a homomorphism. Okay, so there are plenty of that you can see. And so in general, this fm going m going to m square is not a functor for one category object. Okay, so C is not correct. And option D is again a well-known functor. So it's mapping set to set, but here the maps are not. Here the assignment is not mapping the same object to itself. Here you have a set S, you map it to the power set of S. So power set of S is again a set. So again lies inside this set category of sets. So the assignment is map a set to its power set, and how the map arrows are being mapped, and each function from a set x to y is defined uh, element wise over this power set. So what are the elements of this power set? These are the subsets of this domain, right? So u is inside an x, then this assignment maps u to f of u. So this f of u will lie inside y, right? And this sorry, this should be a subset of y. So this is a subset of y. U was a subset of x. So this f of u will belong to fp of y, which is nothing but uh, power set of y. Somewhere it is using f of p, somewhere it is using. So the functor is, let's say, fp. Okay. So this uh, there is some notation confusion. Let me just uh, clarify it for you. So this fp it is using for image under this functor capital F. F is a function from x to y. Then F is mapped to Fp, which is mapping a subset of x to f of u, which is definitely a subset of y. And thus Fp uh, is from f of x to f of y. F of x is what? This is power set of x, and this is power set of y. So it is mapping an subset of x, that is an element of power set of x, to an element of power set of y. So this is the functor, and so you have the assignment and everything, and you can check that it satisfies the properties of functors, and it is known as the power set functor. Power set functor, it's a common name, and it satisfies all the properties of functors. Okay. So A, B, and D are correct, but C option is not correct. So I think now we can move to the second uh, question. Just write the second question. Yes. So it says given a set S, you can define this object list of S be the set of all finite list of objects in S, and from the category set to the category to itself, you can define the functor sending in a set S to list of S. So list of S as defined, it is a set which consists of all finite list of objects in S. Okay, so it is again a set. So corresponding to a set, you can define another set, and that's the assignment uh, uh, being done by this functor F. And how the map is defined? So for each F, that is from the set S to T, we define the map capital F of F from list S to list T by, so list S consists of the finite collection of elements from the set S. So let's say it be x1, x2, xn. This list, any list is denoted by square bracket x1, x to xn, this kind of form, and then it will just map it to f of x1, comma, comma, x of xn, and that's it. So that is the assignment of maps, and the assignment of objects is given a set, you map it to the list of S. Okay, so list of S is again a set, and thus it lies inside this set, and so the maps between these images will also be set 30 maps, and thus they are again inside this category set. So it's a assignment from the category set to the again to the category set, and we have to check uh, uh, whether it's a functor or not, that you can see. Now the question is, which properties does F satisfy? Okay, so the first property is, if F is a map from S to T, then F of R is a map from Fs to Ft for all sets S and Y. So it's a as it's a definition of the assignment is, it is obvious, right? Because you are having, what is f of s? It is a collection of finite list of objects in S. And what is f of t? F of t is a list of objects, finite list of objects in T. So, and you have this small f mapping this object capital S to T, and the assignment is like this. So it is all these elements are inside T, right? So this is inside uh, list T, right? As every element is just an image of the element of S. So it's inside T, and this is a collection of elements, finite collection of element in T. So it belongs to list of T. So it's a map sending a list of S to the list of T. So thus it is a map from F of S to F of T, right? F of S is what? This is list of S, and F of T is just list of T. So just by the definition, this A option is correct. Second, also you can check trivially uh, that F of identity of S is identity of Fs, because how identity will map it to itself. So so this will be just mapping x1, x2, xn to f of x1, x2, f of xn. And what is f of xn? F is identity, so it will be just x1, x2, xn. So it will map x1, x2, xn to itself, right? So maybe this part I can tell. So f of identity over s, it will map x1, x2, xn, a list to the list uh, identity of over x1 comma rn. Here I can do element wise calculation because here the objects are set, but in general I can't do element wise calculation. That is not always available for a category. Here the objects are set, so I can do the element wise calculation. Okay, so identity of x1, it is an identity over s, so it will be just x1, x2, xn. So it's mapping the list to itself. So it's an identity of on f of s. Okay. Similarly, you can check that the composition rule is being it's compatible with the composition rule as well. Okay. And here, what is the initial object? So fourth one, fourth one. So these three implies that f is a functor. Okay. Now the fourth property is a specific property. So one can check the initial object. It's saying it maps initial object to initial object. So the initial object of uh, uh, set is the category set has initial object as empty set and and uh, f of empty set is again an empty set, because if it is not having a element, how will you collect its finite list? So that is again going to be empty, right? There won't be anything in the list of uh, phi. So is again an empty set. So I will just say that f of phi, that is list of phi, is an empty set. So it takes initial object to initial object, right? Initial object was the empty set and empty set is taken to empty set. So D is also correct, right? So all four options are correct for this option. Now maybe we can move to the third option part, third question. So let met Met R denote the category whose objects are positive integers. So here the objects are positive integers, and arrows are a positive integer is mapped to another positive integer, and the arrow is uh, the matrices in R, capital R, this real number n cross m, with composition defined by multiplication of matrices. So first of all, let's understand what is the category. So this m and this n is a positive integer. It belongs to z positive, and it again belongs to z positive. And what are the arrow? This arrow is, is an element of matrix. This is an element of m n cross m. So it's a matrix of order n cross m. So this is the arrow, the assignment from m to n. So any such matrix is an assignment. Okay. So that's what the category is, and the composition is the composition, the multiplication by matrices. So this is a arrow. If you have want to compose it with some other arrow, then you just multiply the matrices, and you can see that it's a category. And then for that category, the mapping is defined like that. You take the category and you define the map to itself, which takes each object to itself. So object is being kept as it is by this assignment. Okay. And given an arrow A, means given a matrix in uh, M cross N, you map it to A transpose of A. Okay. Then the map satisfies uh, these properties. So now one has to see that what properties does this satisfy. So let me just check that for you. So it says if F belongs to met R M cross N, means F is an arrow from uh, so F is an arrow from M to N. So this implies that F is a matrix. Okay, it's using uh, R cross M. M cross N. So it's in N cross N, not N cross N. I was using. So yeah, that's just a notation. So it's a matrix in R. R also I should write here. Yes. Okay. Then f of f belongs to this for all positive integers m and n. So if f is a matrix in this, then f f transpose f is again inside m and cross m r, that you can easily see, and that's why the this is what capital F of f is, right? So f capital F of f is again inside m and cross m r. So first one is correct because f is having n cross m order, f transpose is having m cross n order, and this f will again have n cross m order, right? So their multiplication will have m cross m order, right? And here these two are same, so we can multiply them, and their multiplication will have n cross m order. So it again belongs to m of n cross m r. Okay, so the first property of the functor is being satisfied. Now we have to check b and c. So b says f identity is identity of fn for every positive integer n. So if you have the what is identity of n? So this is just in belonging to m n cross n r, and f of in is in in transpose and then in. So these are identity again. So it is identity and over fn. Okay. Object is being mapped to itself. So n is same as f of n, right? That is what they are. It which takes each object to itself. So n is same as fn, so it's an identity of over fn as well. So this option B is also correct. Okay. Now, if C is correct, then we can say that it's a functor. So C is it satisfies the it is compatible with the uh, composition. Fg of f is Fg compose ff. For all arrows, f belongs to this. So let us see if it is true. So what is F compose G of F? So first of all, you should understand that G and F. So what is F belongs to mat R Mn, and G belongs to mat R and K, means this implies that F is a n cross n matrix over R, and G is a uh, K cross n matrix over R, right? So their composition is F compose G or G compose F? G compose F. So G compose F belongs to G compose F will belongs to, so it's not given, but we can see, no problem. So F will be from, so it's just a multiplication, GF. The composition is just the matrix multiplication, and this will belong to multiplying G with N. So this will belong to M K cross M. Okay. So now what this functor will do, F G of F is what? This is F GF, that is a matrix GF, and it will map it to GF, uh, GF transpose and G of F. Yes. Then you have GF transpose, and then you again have GF. So this is GF, F transpose, G transpose, GF. And one can easily check that uh, this is not, uh, in general, this is not equal to. So let me just write FG compose FF also, then you will have a better understanding of what we are trying to do. FG is G transpose G, and composition is multiplication simply. F is F transpose F. So this is G transpose G, F transpose F. So you can see that these two are different, and in general they need not be same, right? In general, they need not be equal, right? Because matrix multiplication is not commutative in general. So that's why this composition is not compatible with this assignment. So C is not correct, and thus F is not a functor. So D option is also not correct. D is also not correct. Okay. Yeah. So I think with that we can move to the next question, which is already been in some sense discussed in the class. I will just say the solution, final answer. So it's a true false question saying that all functors take initial objects to initial objects, but that is not the case. The simplest counter example is, if you consider a category and the opposite category, so consider the opposite functor from a category to its opposite category. So there the initial object will become a final object. So it won't be taken to the initial object again. Category. So this is a counter example. So we have false. It's just that you just use the definition of that functor and it will come up. That we can move to the fifth question. Says, so I skipped the example of a category associated to the posets. Maybe now I can define that example. So given a poset, you can define a, so poset is a partially ordered set. So a set with some partial order. The partial order means it is the relation is reflexive and antisymmetric and transitive. So antisymmetric means if A is less than B and B is less than A, then A is equal to B. So and the transitive and reflexive, I hope you all know very well. So uh, given what to say, given a poset, you can define a category, and how you can do that, maybe I can just recall it for you. Recall uh, given a poset, say P with partial order A, we can define a category this notation I will use, or they are using this, so I will go with that. Category this, and uh, in which the objects are elements of this poset P, or elements of P, and how the arrows are defined. Given two elements P, or here the two objects of P, uh, this set of arrows is this. So you have a singleton set of arrows, means you have just a single arrow, a name defined as APQ. It's just a naming for a single arrow. If P is less than equal to Q, and this is that the collection of arrows is empty, means there is no arrow otherwise. Means if P is not less than equal to 2, then you have no arrow, and if P is less than equal to 2, then you P is less than equal to Q, then you have a single arrow, which is denoted as AP of Q. Okay, so and how the composition map is defined here, given PQR belongs to uh, the object set, that is P, such that P is less than equal to Q less than equal to R, so only then the if on- only with this condition you can define composition. Now, if any one of them is not satisfying less than equal to condition, then the arrow empty set is uh, the collection of arrows. So there is nothing to be defined. So at least there should be an arrow from P to Q. So P is less than equal to Q we are choosing, and at least there should be an arrow from Q to R. That's why we are taking the uh, condition Q less than equal to R. Okay, because at least one arrow we need. So there APQ is the arrow from AP to Q, and AQR is the arrow from Q to R. So the composition is APQ composed with AQR is APR. So this is the composition of arrows. Okay. So this defines the category, and now for that we need to check whether which of these statements are correct. So first one says that if x is less than equal to y, then fx is less than equal to fy in Q. So we have the category P, and with the defined by the poset P, and then we have the category Q defined by the poset Q, and so any element x is mapped to fx and any element y is mapped to fy through this uh, functor capital F. And it's saying for every functor we have to check, not for a single functor. It, the properties we have to check for every functor. So yeah, how we can do that? First one
Sir,
is yes, Vivek. Hello.
sir, this is the definition that I am claiming for this question. AQR and operation APQ is equal to APR.
This is in general given a poset, you can associate a category in this manner. This is the associated category for a poset. In the
Means
question
this
you
is
have,
it's always fixed like that.
yeah, it's
AQR or A.
yeah, it's standard for any poset. You define an associate category in this manner.
Okay, sir.
So uh, given an objects P and Q, you say define a map with the notation APQ. Maybe the notation you can change depending on your comfort zone, but the idea is if P is less than equal to Q, then there will be a single arrow, and if P is not less than equal to Q, then there won't be any arrow. So that's the collection of arrows. Okay. So first one says f is if x is less than equal to y, then fx is less than equal to fy in Q. So how to check first? So x less than equal to y in P implies that the collection of arrows from x to y is a sorry, here I will have a x comma y, means that is not empty, right? So this implies
Yes,
that
sir.
f of a x comma y, this is a arrow from the other category is capital Q. This is an arrow inside. Maybe I will use this for the category. So this is from fx to fy. So since this is not empty, so the collection of arrows from fx to fy is also not empty. And since this collection is not empty, it implies that fx has to be less than equal to uh, fy in the category y, in the category q. Because if it is not less than equal to that, then this collection has to be empty by the definition. Okay. So the first one is correct, and that's the only option correct, because in for B part you need a functor from we need a functor from Q to P, which may not be always available. You may not have a functor in the reverse direction. So B is not may not be correct in general, and thus B is not correct. So this is if and only if condition. So C is not correct as well. Okay, and it says none of these conditions, but A is already correct. So D is also not correct. Okay, the idea here is to smartly use the category associated with the posets. Okay. Okay, so maybe then we can move to the question number 6. 6 is a bit larger question, so we will read it very carefully. Yes. So it says, let C be a category with two objects, A and B. So they're just two objects and three arrows. First, so see, two arrows are mandatory. If there are two objects, two arrows are mandatory by the axioms of the category, and that these are the identity arrows, because in one of the in the one of the axioms in the definition of category was that there should be an identity arrow for each object. So these are the two mandatory arrows, identity over A and identity over B, and we have a third arrow that is mapping A to B. That's it. Okay. So there are just three arrows. You have from A to A, that is identity, B to B, that is again identity, and then A to B is a single arrow is there from A to B. Okay, they are not more than one. And composition are uniquely determined, because how will you compose in that trivial situation? Identity with this arrow is again this arrow, non-trivial arrow, and so what I mean that if you compose identity of A with phi, then it will be phi again, right? And if you compose identity of B with phi, then it is phi again. So these are the two composition possible. Okay, and they are just determined by the identity property of identity. Okay, so then it's saying consider the arrow f from z to z in the category of z modules. So uh, given by f of n to 0. So z is a uh, z module itself. So you are considering the category of z modules. So z is an object there because z is itself a z module. So from z to z, you are defining the map, sending each uh, element of z to 0. So here we can consider it element wise because z is a set. Okay. In particular, the object may not be a set. So for all n belongs to z, you are mapping everything to 0. Then they are defining a functor uh, f from C to Z modulo. So this is Z modulo, category of Z mod, category of all Z modules. The name for it is Z mod, and C is our category with two objects and three arrows. So from C to Z modulo, the map is like that. The assignment is like that. So there are two objects, so you need to define an assignment for those two objects. So A and B both are being mapped to the module Z. The identity map is mapped to the identity of Z, and identity map B is mapped to the identity of Z again, and then this non-trivial arrow is mapped to F. Then the functor F, one has to say whether it preserves monomorphisms, preserves epimorphisms, and then preserves monomorphism and epimorphisms. So see, if C is correct, then A and B both are not correct. And also D is not correct, right? Because it preserves monomorphism and epimorphism both, then this only will create problem, right? And then of course it's then D is not correct. So we will try to show that C is correct.
Sir, Z module here, that means category of Z module.
See, category of Z
That
modules,
is like
all
like a
modules, all modules over the ring Z.
over the ring, yes.
Over the ring Z, uh, whatever modules are possible, that will, for example, all abelian groups, they are all modules over the ring Z, right? So they will come with the module structure inside this category. So it's the collection of all
Okay, that is
modules over Z.
defined in the set of integers.
Ah, the modules over
Okay, okay, right.
the ring of integers. And Z it itself a module. Every ring is a module over itself, right? So
Yes.
actually, I think
Okay, sir, fine.
this part is also wrong and this is correct. It preserves neither monomorphisms or epimorphisms. And for that, the example is, so we have to find an example which is a monomorphism and which is not preserved under this functor, and an epimorphism which is under, again, not preserved under this functor. So uh, claim that f is a, uh, sorry, so we have to consider a monomorphism inside this C, right? Because this is the domain. So the only non-trivial morphism we know is phi, right? So we will claim that phi is a monomorphism and epimorphism in C. What was the definition of monomorphism? Let me just go back a bit. So an arrow is said to be a monomorphism if it allows
F
the left,
of G is equal to F of H.
implies
That
G
is
equal to
left
H.
cancellation law.
So left cancellation is allowed and epimorphism means right cancellation is allowed.
Yes, sir.
Okay. But for phi, what is the possibility that you can, uh, the only way to compose phi from right is by identity of A, right? Because there are just three maps. Phi cannot be composed to itself because phi is a map from, you just consider this situation like that. So there are two objects A, B. You have from A to A the identity of A, from uh, B to B the identity of B. Yeah, I should use small a. Okay. And then from uh, A to B, you can map it through phi. So how can you compose phi from right? So it's a map from A to B. You cannot compose it again by phi because phi is not from B to A. So only way to compose it by right is by identity of A. That's the only way you can write something of the form phi compose identity of A, because you have to start from A and then again end from A, end at A. There is no other object. So uh, this implies phi is trivially a apomorphism. Sorry, monomorphism, because there is no other option. You for monomorphism, what we were doing. So let me again take you back to the definition of monomorphism. Yeah. So we were cancelling it from left side. But if there is no possibility for G and H, rather than the only possibility is a single possibility, then this is trivially true, right? You can compose it from right only, say, by G, then f of G equal to f of G implies G equal to G. This is trivially true, right? There is no such H different from G for which you can even compose. You got the point? There is just one morphism, there is just one arrow using which you can compose it from right. So this is like trivially true. There is no other option. So how will you like discard the equality? It is always equal. And the only way to compose phi from left is by identity of B. Here also, phi is from A to B, then from B, you have only one map. Phi is from A to B, and then from B, you have only one map, which will land again to this B. So here also it is vacuously true. Okay. So did you get the point? So you have a map from A to B. Then if you want to compose it from right, you should have some map which is landing on A. So there is only one such map which is landing on A, is the identity over A. And if you want to compose it from left, then you need a map initiating from B, and that the only map is such map is identity over B. So uh, you have only one option, right? That is identity over B over phi, right? Phi is from A to B, then you have identity of B from B to B. There is only such map, one map which is initiating from B, and here also there is only one map which is terminating at A, that is from A to A, and then from this is from A to B. So here also this is trivially a apomorphism. It's trivially a apomorphism. Okay, so phi is a morphism and epimorphism. We have to show that uh, uh, this is also a this is not preserved inside this capital F. Okay, that then only we can say that capital F preserves neither monomorphisms or epimorphisms. Yeah.
So, sir, option C or option D is the right choice.
D is the correct choice. It preserves neither monomorphisms nor epimorphisms. So we have first found an
So just
epimorphism and monomorphism, that is phi, and we will now show that f of capital F of F is neither a monomorphism nor an epimorphism. So
okay,
uh,
whether left or right, both are not true.
yeah, so for claim is capital F of phi is neither a monomorphism nor a nor an epimorphism. So I will just show the epimorphism part and leave the monomorphism part for you. So for apimorphism, you need two maps. So we will define two functions from Z to Z. So pick. So our A and B both are mapped to Z. So we have to consider the maps from Z to Z itself, right? So pick two functions, G1 from Z to Z and G2 from Z to Z, such that the definition of G1 is Z1 of X is G1 of X is 2X and G2 of X is 3X, right? So uh, so G1X is clearly not equal to G2X, implies uh, I will directly say, so G1 is not same as G2, right? But what is uh, G2 of F? G1 of compose F is nothing but a map from, so F is mapping from Z to Z everything to 0, right? Then this will again be a map from Z to Z such that mapping every X to 0, because F is map X to any X to 0 and then G1 is just twice of this, that is 0 again. And Z2 of F is again from Z to Z. So F of 5 was F, right? This is the functor maps this phi to F, right? So we need to show that this F is neither a morphism nor no, neither a monomorphism nor a epimorphism, right? That's why I'm taking working with this small f. So again, F maps everything to 0 and G2 is just taking the triple of it. 0 will be mapped to 0. So it will map everything to 0. This implies G1 of F is equal to G2 of F. So G1 of F is equal to G2 of F, but G1 is not equal to G2, right? So this implies F is not an epimorphism. Similarly, you can define even for the same functions. If you look at what is F composed of G1, okay, this same thing we can do. Not, I don't think we need it specific for uh, this. Now, consider F compose G1 and F compose G2. What they will be? So F compose G1 will be from again Z to Z, and G1 is mapping every element X to uh, 2X, and then it is mapped to 0 under F, right? Similarly, F compose G2 is from Z to Z. Z2 is mapping X to 3X, and then under F it is being mapped to 0. This is mapped to 0. So this implies F compose G1 is also equal to F compose G2, but we know that Z1 is not equal to Z2. So F is not an epimorphism. So, sorry, not an monomorphism. So this functor neither preserves the monomorphism and nor it preserves the apomorphism. That's why the option D is correct and A, B, C are incorrect. Okay. Can we say in category Z modulo, monomorphism reduces to one functions and apomorphism reduces to onto functions as modules are just sets and the end. F is neither, so it doesn't preserve. Uh, See, that is true only in the category of sets because in general, injective doesn't mean monomorphism and surjective doesn't mean apomorphism. We will see such an example in the category of rings. Something that is true in the category of set, you cannot lift it to the category of groups or rings or modules. You are right that in category of sets, epimorphism means surjective and monomorphism means injective. But uh, in general, that is not true. Okay, so there is. I will give one such example. And in fact, the next question is such an example. So the forgetful functor f from ring to set preserves epimorphisms. So what are the epimorphism in set? They are surjective maps, right? So in set, uh, epimorphisms are same as surjective maps. But rings, for rings, it is different. And how, uh, this should be false, I think. This is false. Why is it false? So, example is the inclusion map from Z to Q is a is an epimorphism. In ring. So you can see that this map is not surjective, but it will satisfy the property of being an apomorphism in the category of rings. Okay, so this is uh, in ring it is apomorphism, but not in a set. Not in set. And in fact, this was shown in the last assignment. So this is the example. So inside, it is easy to see why it is not a apomorphism. So here, definitely this part is easy to do since uh, I is not surjective. For set, it is easy to see that it is not an epimorphism because for sets, injective means injective if and only if monomorphism, and surjective if and only if epimorphism. But in drinks, it is not like that. Okay. So this I think clarifies your doubt, Adarsh. Okay. Okay. So now we can move to the eighth question. So it's a bit lengthy, but uh, answer is small. Okay. Maybe I will need a separate page. Let's see if I can manage itself. Doesn't look nice, right? So maybe uh, I will move to the next page and then paste it. It's very, very big, so it's getting problem. Yeah. So it says, let C be a category where C of AB is the set of all objects AB of C. For a fixed object A of C, define a functor FA from C to set by. So what is the arrow? Uh, Arrow is a set for all objects AB. Okay, so whatever object you have A and B in this category C, the collection of all arrows is a set. Okay, so the functor is from C to set. You define it like that. You fix the object A and you map the object B to C of AB. This C of AB is a set, so it lies inside this category set. And what is the underlying map? You map F from B to C and G from A to B to just F composed of G. So this is the composition map. So then it's saying consider the following proof of identity being mapped to identity, and then where is the error in this proof? So first step is saying you must prove that F of A identity B is uh, so it has to be identity from F of A of B, right? So what is F A of B? It is C A of B. So it should be identity from C A of B to C of A, C A of B, right? So this part is correct, is the identity map. And identity map in the category set takes each element of the set to itself. So we must prove that F of A identity B of G is G for all G belongs to C of A. So it is just the definition of identity map. So there is no error in step one. Second is saying identity B compose G equal to G uh, for all G belongs to C of AB. That's what we need to prove, right? So this is also correct. The third step says given to prove that given G belongs to C of AB, for all A belongs to A, we have this. Now this step is a problem. Why? Because here we are considering A as a set, right? That if it is a set, then only we can say uh, that something belongs inside it, right? As I gave you the example of a collection of students in a class, how can you find an element inside a student? No, right? So here we are considering A as a set, which is not true in general. So this question was to tell you that you cannot use the set theoretic things for objects in an arbitrary category. The objects of an arbitrary category may not be set, because here we just say C be a category. The objects here may not be the sets. Here we are considering A as a set, which is not true in general for an object of a category. So this was a mistake. Okay. So error in step third is the correct option. Okay. Now, ninth question is just a definition. Nothing specific. Yeah. So a category whose collection of objects and collection of arrows are both sets, we say such a category to be a small category. So that's a name for a category in which every object is a set and the collection of arrows are also sets. So the answer is small. Okay. Then uh, we will quickly see one or two more questions. Let me just put my charger. So I haven't defined what is a natural transformation. So I leave it to you guys to who haven't not seen the definition of natural transformation to go and see the natural transformation. Okay. So what I was saying that I haven't defined what is a natural transformation, and it takes some time at least to define what is a natural transformation. So those who have not seen the lecture notes, I request you to kindly see the lecture notes after the uh, uh, class is over, and I will just give some ideas of to question number 10, 11, and uh, uh, 12, 13, even 14, because we are already out of time. So I won't be solving them completely. So it says, let's see, denote the category with one object. Yes. So 10 question says, let's see, denote the category with one object, and C star is S3. So the arrows are defined by the elements of S3. The symmetric group on three letters, composition of arrows coming from the group operation, and S, let S equal to 1, 2, 3 belongs to S3, a 3 cycle. We defined a functor from C to C by just sending this single object to itself. That's the only way we can define it, right? And then how the maps are being defined? Yes. And each arrow is an element from S3. So it is being mapped to SG S inverse, the conjugation by this S, 3 cycle. Which of the following is a natural transformation from F to F? So for a natural transformation, what we need, uh, so I will say for natural transformation, between the functors F and G, an assignment Nita uh, should do uh, should make the following diagram commutative. What is the following diagram? So you have some f of uh, a, and then you have some g of a. A is any object, right? And neta is maps f of a to f of b. From f of b to g of b, you have neta of b, and from here to here, you have f of f, and from here to here, you have some g of f. And this diagram should be commutative for all AB belongs to the object of this category C, and F belongs to C of A comma B. And here uh, F is a functor from sorry, F and G are both functors from the category C to D, to some category D. So such a transformation is a natural transformation. Okay, a transformation which relates two functors. So what functor was doing? Functor was relating two categories, and what is a natural transformation does? So it relates two functors in this manner. So in our case, C is equal to D. We are here with only one category, and also F is equal to G. We have to see, and n of A is n of star, because there is only one object, is equal to n of B, and A equal to B equal to star. There is only one object, right? So we just need to check that f of star uh, and of course this uh, f of star is also star, and f of star is equal to star, and what was uh, f of f? F of f is s f s inverse, right? So we want f of a is f of star, which is star, and then g of a is f of g is same as f, which is again will map star. Here also b is equal to same as a, so here also you have star to star. So you have neat of star here, here also neat of star, star to star. You have f of f, which is s f s inverse, and here also you have g of f, which is f s f s inverse. So we want the commutativity of uh, this map, this diagram, which is S, F, S inverse. So we want this diagram to be commutative. So we want N star S, F, S inverse to be same as S, F, S inverse N star in S3. Okay, and how we can get that? So this is not true if N star is S or S inverse or 1, 2, because it has to commute with this SF S inverse for all F belongs to S3. This is not for even for one uh, single F. This is for every F. This is for all F belongs to S3 we have to satisfy. So uh, this is not true if n star is equal to S inverse or 1 by 2, and uh, you can check, you will definitely find one f such that it won't be satisfied if n star is of this form, and it is true when n star is identity. So that's why the only B option is correct. So be aware that in the solution sheet, the answer is totally different, and this is the simplest way you can answer this. There was some mistake in the solution sheet. I don't know whether they have released it till now or not, but there was a mistake. So you can just follow this solution and it's correct. Okay. Now, question 12, sorry, 11. So just follows from the notes, which of the following prevents the formation of category of categories? So in the lecture, it was defined a category of uh, uh, considering the small categories, not for arbitrary categories. So the paradox which uh, prevents this is the Russell paradox. Okay, so it's just a one-word answer. So I won't say much about it. And then uh, I think I can leave 12, 13, and 14 for you guys. You can try 12, 13, and 14. And if you have any doubt, then you can ask me in the next class. Let's say try 12, 13, and 14. They require one or two definitions to be understood. 14 in particular require the definition of adjunction, and which is clearly written in the lecture notes. So you have to go through the definition of adjunction to actually know what is this. So or an adjoint pair. So the adjoint pair and adjunction both you need to learn before handling 14, but 12 and 13 can be I think can be done with whatever we have discussed till now. Definition of natural transformation will be needed, which I roughly defined. So you can try 12, 13, and 14, and then let me know if there is any issue. In the next lecture, we will. So, is my screen visible or it's been paused?
Visible, sir.
Okay. So yeah, so that's what I'm saying, that you can try 12, 13, and 14. If there is any doubt, then you can ask me in the next lecture, and otherwise we will start assignment number 9 in the next lecture. Okay, and that is not using category, it is based on the some module theory, so you can independently read that. Mm, not much will be required from this lecture and the last lecture. So even if you have not understood these two lectures in a very well manner, still you can come up in the next lecture in, and see the solutions. Okay. uh, is there any doubt?
No, sir. Clear.
Okay, so then I will stop here. Our next lecture will be on next Tuesday on 9 at the same time, 6 to 8. Okay.